Welcome back to Analog Electronic Circuits. Today is the second lecture, and we are going to talk about diodes, and then if there is time we will start introducing the transistor. But first we are going to talk about a few circuits with diodes. In the last class we had given an introduction to different abstractions for the diode. So, the diode is basically a PN junction. However, we are not really as a circuits in a circuits class, we are not going to be interested in what is going on inside the diode. We are going to look at the overall I versus V graph, and the overall I versus V graph we had three abstractions. The ideal one in the last class, this is the diode that I wished to purchase, but could not find in the market. This was the ideal diode. Then the diode that I believed I purchased, or a second level abstraction, was something like this, and a third level abstraction, which is the actual diode, is something that looks like this. Okay. So, mathematically we represented, we had this also in between. I am sorry, we had this also in between. Okay. So, we represented the green curve, the blue line, and the blue dashed line mathematically, and the last dashed line has to pass through 0, and with that it came down to, it boiled down to something like this: I is equal to I naught times e power v by Vt minus 1, something of this format. Okay. All right. Now, this is as far as the diode goes. These are the three models for the diode. The diode can be used in a circuit. So, imagine a circuit that looks like this. Okay, and you are asked to compute the current. How will you find this out? So, the first question that you are going to ask is, what is this diode? Is this diode an ideal diode like the green line? Is it a diode like the blue line? Is it one like the red line, or is it the blue dashed line? So, let us do it step by step, right. So, what engineers do is, first they do the 0th order approximation, then they do a first order approximation, then they do a the more difficult one if required, and finally they do the exact one only if absolutely required. So, normally they will not bother about the exact curve. Okay. So, let us do the green one, the green line over there, the ideal diode that I wished to purchase. So, if you think about that diode, then all you have to work out is this diode on or off, because if it is on, then the drop across it is 0, whereas if it is off, then the drop across it can be anything and the current will be nothing. Okay. So, the current, if at all, is going to go in the direction of the arrow, which means that the diode is probably on. Okay. You can verify by contradiction. Let us say that the diode is off. All right. If the diode is off, no current is going through it, but any voltage can appear across it, any negative voltage can appear across it. So, if no current goes through the diode, then the drop across the 1 kilo ohm is 0, and then the drop across the diode is 5 volts, but that is not negative, right. It is not negative. So, we have to be in the negative axis if no current flows through it. It can be any drop as long as it is negative, but this is a positive drop, which means that our assumption is not true. So, therefore, the diode has got to be on, not off. So, this is incorrect. The diode is on. If the diode is on, the drop across it is 0. If the drop across it is 0, then the current in the 1K is 5 milliamperes. Okay, done. This is method 1. Now, let us work with the second approximation. Let us say that this diode cut in voltage is 0.7 volts. So, this is a very safe approximation if we are talking about silicon. A silicon diode normally has a cut in voltage of around 0.7 volts. In such a scenario, what is going to happen? Is the diode on or off? Once again, if it is off, then the drop across it is positive, which means that it has got to be on, because positive voltage is not going to be sustained. It is 5 volts across, certainly more than 0.7 volts, and therefore current has to flow. That means the diode is on. Now, if the diode is on, the drop across it is 0.7 volts, and therefore the drop across the 1K is 4.3 volts, which means that the current through the 1K is going to be 4.3 milliamperes. So, look at my answer. First answer was 5 milliamperes. This was the 0th order ideal diode that was not available in the market. The second one gave me 4.3 milliamperes. Okay. And then you say, all right, let us not worry about these approximate answers, let us try to work out the precise answer. Okay. So, now I am going to attempt to work out the precise answer. Okay. How do I do it? KVL. We will write a KVL. So, 5 volts is equal to the drop across the diode, let us call it Vd plus Id times 1K. Okay, and as long as Id is in milliamperes, if I choose the units of Id to be in milliamperes, then 1 is fine. Okay, so this is my KVL loop equation. The other thing, of course, is that Vd and Id are related to each other, but let us not worry about it right now. Okay. So, let us try to plot this equation on these axes. So, this particular equation is what I want to plot. 5 is equal to Vd plus Id times 1. Can you plot this on this on these axes Vd and Id? How will it look like? Will it look like a circle, parabola? What is it? What is this an equation of? 5 is equal to, this is the x axis, and this is the y axis. Yeah, this is a straight line, right, and this is a straight line that obviously looks somewhat like this. When you say Vd is equal to 0, Id would be equal to 5, and if Id is equal to 0, then Vd has to be equal to 5. Okay. So, these points, these intercepts on the x and y axis are 5 milliamperes and 5 volts respectively. Okay. So, this particular graph where you have worked out a KVL and you are writing out you are plotting out the KVL, this is called the load line. So, the load line is a very important concept. It has nothing to do with the device equation. It is purely based on KCL and KVL, right. 5 is equal to Vd plus Id times 1. Here there was no there was no diode involved, right. It could have been a diode. This need not have been a diode at all. This could have been any other device of your choice. This diode could have been forward biased, reverse biased, whatever you want, right. This equation is always true, and this is coming purely from KCL and KVL. Okay. So, this is I have drawn it in blue, but this is a golden line, as in this is the absolute truth. KCL and KVL are always true, which means that this load line is always true no matter what that device is and what is going on inside that device, right. Whether that is a PN junction diode, whether that is not a diode, whether it is a vacuum diode, whether it is some other air gap, whatever it is, right, this is always true. All right. Now, with this understanding, the next thing that we do is we plot out the diode characteristics, and look, think about it once. The way I have done it, the diode characteristics need exactly the same variables Vd and Id, the same axis, right. So, on the same axis I can plot the diode characteristics, and the diode characteristics are going to look like this. All right. Maybe it is not so bad, maybe it is something that looks like this. Yeah, this is better. Okay. In which case we can work out what is the point of intersection between the diode characteristics and the load line. The load line is the absolute truth. Whatever happens to the device, this has to be correct. KCL and KVL have to be satisfied, which means that Id and Vd always have to lie on this straight line. Now, you bring in the diode and say that because it is a diode, it has to follow this red graph. And now, if it also has to follow the red graph, then the only point that satisfies both the red graph and the fact that it has to satisfy KCL and KVL is this point of intersection. So, this is the actual point of operation. All right. And invariably what you are going to find is that this actual point of operation is going to be quite close to this second number, all right, and the second number is actually a very good approximation of the exact result. All right, is this technique understood? So, this is called the load line technique, and the reason why we are studying diodes at all is one of the big reasons why we are studying diodes at all is to understand this technique, this load line technique, because the load line technique is going to appear in all kinds of places everywhere. I mean, without any warning I am going to start drawing a load line, and then you have to recall what you studied in this diode lecture. Okay. So, is this load line technique understood? All right. Few more circuits with diodes, some things that you already know. One popular circuit is the rectifier. This is a very popular circuit. This is called the half wave rectifier. What happens in this? So, this is a sine wave. The input is now a sine wave. What is the waveform? So, if we use, let us use our the second rule, right. We are going to go by this most of the time. We are going to make an approximation that the silicon diode conducts when the voltage is beyond 0.7 volts and does not conduct when the voltage is below 0.7 volts. So, let us make this approximation and proceed. Okay. So, this is time, and the input voltage is a cosine that looks like this. Okay. What is going to be the result? The diode will have a drop of 0.7 if it is on. If the diode is off, the drop it can sustain any drop as long as it is backwards, as long as the drop is negative. So, in the positive half cycle, during the positive cycle of the sine wave, there is a likelihood that the diode will be forward biased, that it will sustain a drop of 0.7 volts, and that will happen only beyond a level of 0.7 volts. Suppose this is 0.7. So, only above this level you are going to get a forward bias current, below this level you are not going to get any current whatsoever, right. So, if you think about it, the drop across this resistor is just this portion, and then when it is reverse biased, the drop, there is no current, which means the drop across the resistor is 0, and so on and so forth. Okay. So, here the 0 is over here. Any questions? So, this is I did it a little fast because this is, you have probably studied this many times before. This is called a half wave rectifier. Great. Now, somebody wanted to make a full wave rectifier. How will you make a full wave rectifier? Yes, your favorite circuit, full wave rectifier circuit. There are two full wave rectifier topologies. One is probably your favorite, so this is called the bridge rectifier. So, when the voltage is positive, it appears in this fashion, okay. But when the voltage is negative, it conducts in the opposite way. Have I made a mistake? I think I have made a mistake. Okay, let me draw it the ordinary way of drawing it. I think this is not correct. So, the way you are going to draw it is yeah, this is a better way of drawing it. That is why this is the way it is always drawn. Okay. So, when the voltage is positive, that is when this voltage is more, right, when the polarity is this side is plus and this is minus, then current flows in this fashion. Okay. Through the two diodes. However, when the polarity is reversed, when I have plus on the other side and minus on the other side, okay, I want the same current, the current to flow in exactly the same direction, and therefore, what I do is I place two more diodes and now the current goes like this. Okay. So, that is when the polarity is reversed. Fine. Is this understood? So, this is called the full wave rectifier, and you have studied this before, exactly like the half wave rectifier, but now it operates on both cycles, both half cycles. Okay. So, this is the green and the red are corresponding to the voltage drop across the resistor in the two different cycles, half cycles. So, what I have drawn on the graph, this x axis is time and the y axis is voltage. So, this is your input voltage, right, and this inset, this is the voltage across the load. So, that is what has been drawn in the graph, and the gap between the two is 2 times the diode drops, right, 2 times the diode drop, because there are 2 diodes that appear in series. All right. So, this is called the bridge rectifier. This is also a very familiar diode circuit, and there is also one more topology for the full wave rectifier, with it has a transformer in it. So, we are not going to bother about it right now. There is one nice circuit called the peak detector or the envelope detector, and that is an offshoot of the half wave rectifier. Let us quickly take a look at that. So, this is the standard half wave rectifier. Okay. This is the standard half wave rectifier. Now, what I am going to do is I am going to add a capacitor across the output terminals. So, I have added a capacitor across the output terminals. For a second, let us even forget the resistor existed. So, let us forget about this altogether. Now, what is going to happen? Basically, I replace the resistor with a capacitor. Actually, they can coexist, there is no problem there, but let us just throw it out. Now, what is going to happen? So, suppose this is the waveform of V in of t, and let us say that the diode is an ideal one that I could not really find in the market. Let us say that it is an ideal one. So, the drop across it is nothing if it is forward biased and it can sustain any reverse bias voltage. Okay. So, under these circumstances what is going to happen? Let us define a starting point. We have a capacitor. So, the capacitor should have an initial condition. Let us give it an initial condition of 0 charge. So, at time t equal to 0, the charge on the capacitor is nothing. Let us start with that. Okay. Now, what is going to happen? In the forward cycle, the capacitor, the current is going to flow in the forward cycle, and the capacitor is going to slowly charge up all the way to the top. Correct? Any problem with that? No problem. But when it comes to dropping down, the capacitor has to discharge, and when the capacitor has to discharge, the current has to flow backwards back into the source. Is that right? Now, if the current has to flow back into the source, the diode is not going to allow that, which means that this capacitor is allowed to charge up but not discharge. So, therefore, since the current can't go backwards, this is going to continue. This voltage is going to be held for how long? No current all the way in the discharge path, and then during this period, during this half cycle, there is no current anyway because the diode is reverse biased, which means that the next time this voltage comes back up, now there is an opportunity for the capacitor to charge. Maybe it might charge if it has reason to. So, this voltage is going to continue to be held, and if in the next cycle it goes beyond that voltage, then only there is some charging that is going to happen. If it does not go beyond that voltage, then this is just going to continue. Okay. So, this is called the peak detector. Right, it just detects the peak, the maximum of V in of t. Okay. Now, let us throw the resistor back in. So, this resistor is now back. Now, tell me what is going to happen? Yeah, what is going to happen? It is the same thing, just that that capacitor now can discharge through the resistor. So, yes, it charges up, it charges all the way up, but when it comes to discharging, there is now a path for the capacitor to discharge through the resistor, okay, and that will have a time constant of R times C, right. And if RC is large enough, then maybe it will not completely discharge before the next cycle hits it. So, in the next cycle again it will charge up, and then again it will slightly discharge till the next cycle hits it, and again it will charge up, right. So, this way every cycle it can, the circuit works out its new peak, every cycle, right. And this kind of a circuit, if you think of many cycles, then it just follows the envelope of the signal. So, this is called an envelope detector. This is uh, the technique that used to be used long back for amplitude modulation, demodulation, amplitude demodulation, right. This used to be the technique. How? Okay. So, what is amplitude modulation? You just have your message, suppose this is your message signal, and this m of t is going to be multiplied by the carrier, right. Actually, m of t plus a constant is going to be multiplied by the carrier. When you multiply by the carrier, effectively what you are going to do is and remember the carrier frequency is much larger than the message signal, right. That is how it is. So, you have your m of t plus a constant, this is getting multiplied by f naught. Okay. So, this sine wave is at f naught, and this overriding signal is m of t plus that constant plus 1. So, this is your traditional amplitude modulation, and now you pass this signal through my envelope detector. So, what is my envelope detector? It is nothing much diode, capacitor, that would have been the peak detector, just the diode capacitor, but I will also put a resistor such that in every cycle the RC time constant C R and RC is such that in every cycle it falls a little bit but not completely, okay, so that the circuit is able to work out a fresh peak, the fresh amplitude. So, what is going to happen? Let us do it with a different color. So, first it is going to track and then it is going to start falling, but in the next cycle it again tracks, falls, tracks, falls, tracks and falls, right. Overall what you see is it is more or less going to find out, work out what the envelope of the signal almost, okay, and that is the message. So, you have kind of worked out the message signal. All you need to now do is low pass filter this and clean up the kinks, get rid of the DC component, and there it is, your message is ready. So, you have to low pass filter this. So, RC is already a low pass filter and you just have to choose the time constant nicely, so that it does the job, and then you have to remove the DC, that is you put a blocking capacitor and remove the DC, and that is it. Then you amplify it and send it to the microphone. So, this is an AM demodulation circuit, alright, also known as an envelope detector. So, an envelope detector detects the moving amplitude. of the signal. Great. Okay. So, these were some interesting circuits using diodes. You can also use 2 of the peak detectors to make a voltage doubler. I will leave it to you to figure out how that is done. You can use 3 peak detectors and use them intelligently to make 3 times the amplitude and so on and so forth. So, I am going to leave that to you, maybe that will appear in a homework. Please work it out. Okay. With this I am going to start with I am going to stop talking about diodes. Diodes is not the mainstay of this, not the focus of analog circuits. You can make some interesting circuits with diodes, but you can only go so much because the diode is passive. So, now we are going to start working with active devices, and the transistor is an active device, is an example of an active nonlinear device. Okay. In your undergraduate syllabus there is a transistor called the bipolar junction transistor, that is very popular in the books and so on. However, the BJT has been phased out from most systems. Most systems no longer use the bipolar junction transistor at all, most modern systems. So, if you are in this day and age, you are not really going to be that much interested in the BJT, it is just an academic interest. The more popular transistor today is the MOSFET. So, this is called the acronym is bipolar junction transistor, and over here the acronym is metal oxide semiconductor MOS field effect transistor FET. So, there are many different kinds of FETs. MOSFET is one FET, FET, metal oxide semiconductor field effect transistor, and in this course we are going to focus primarily on the MOSFET. In passing we will mention the BJT just because it is there in your books, and in some exams it might be asked what the BJT is all about and how to work out circuits with BJTs. These things might come in exams, however, beyond exams the BJT is of no relevance whatsoever. Okay. So, I have drawn the symbols so far for the BJT and the MOSFET. These are both transistors, right. This terminal is called the base, the emitter and the collector, and similarly in the MOSFET this terminal is called the gate, this is the source and the drain. Now, there are 2 different flavors of BJTs. One flavor is the NPN, right. This is called the NPN BJT because that is how it is made. It is made with a block of silicon, N type, P type and N type. Okay. So, this is how it is made. Okay. So, that is why it is called an NPN BJT. Likewise, this particular MOSFET, this flavor of MOSFET is called an N channel MOSFET. Or a lot of people in short call it an NMOS transistor. Okay. So, there are two more flavors, there is one more flavor for the BJT, and that is called the PNP BJT. Okay. So, this is emitter is P type, base is N type, and collector is P type. So, this is called a PNP BJT, and similarly there is another flavor of the MOSFET which is called the P channel MOSFET. And a lot of people call it the PMOS transistor. Fine. So, there are a few more symbols that I am going to draw, and all of these symbols are equivalent. So, the BJT, this is the only symbol, right. Some people draw a circle around the BJT, but that is okay. You need not draw the circle around the BJT, it is still exactly the same as the BJT. For the MOSFET, there are a few more symbols that a lot of people use. One popular symbol that is used in a lot of digital circuits is just this, without the arrow. If you draw it like this is actually let us call it so this terminal could either be the drain or the source, right, because there is no marker. Likewise, this terminal could have been the source, but it could also be the drain, there is no marker. Okay. However, this is the gate. Now, when you draw it like this MOSFET is probably being used as a switch, okay, and when you are using at a switch, the switch is either on or it is off. When the switch is on, it does not matter which is source, which is drain, and when the switch is off, it still does not matter which is source, which is drain. Okay. Either the switch is on, so it is a short circuit, or it is an open circuit. So, the connection between source and drain is either a short or an open, all right. So, that is the likely operation of this circuit when it is drawn, when the MOS device is drawn in this fashion, that is what it probably is being used for, it is being used as a switch. Okay. And this particular device is N channel, all right, that is the symbol. Now, there is a parallel one, and in the parallel one so the gate is the only terminal that is relevant. These two can be anything, either source or drain, right. This particular device is a P channel device, and it switches on when the gate is low. So, there is a bubble, right. Remember your digital circuits, whenever you put a bubble, it implies a not happening. Okay. So, these are also symbols for the MOSFET, but remind you that these symbols are going to be used only under situations where the MOSFET is going to be operated as a switch. So, that means digital circuits. So, these are symbols used primarily in digital circuits. Okay. Then there is one more source of confusion. The MOSFET comes with a fourth terminal. So, there is actually one more terminal in the MOSFET. So, the MOSFET is not a 3 terminal device, it is a 4 terminal device. Okay. The fourth terminal is the body. So, one possible symbol is just like this, another way is to put an arrow, but once again over here, because there is no clear identification which is drain, which is source, this device is probably being used as a switch. In case of the PMOS device, this is N channel. In case of the P channel device, the symbol is opposite. Okay. So, these are some of the symbols. We are not really going to use any of these, right. At best, sometimes we might point out the existence of the body, but mostly in this course we are going to stick with these symbols, right, for the BJT, N channel, NPN, PNP BJTs and N channel MOSFET, P channel MOSFET. This is what we are going to stick to most likely, right. Sometimes we might show this symbol if we want some special work to be done with the body. Okay. Now, with an understanding of these symbols, let us also point out a few conventions. So, in electronics, in your circuit theory course, whenever you have drawn circuits, you might have drawn circuits like this. Right, you might have drawn complicated circuits like this and you would have been asked questions to analyze and so on and so forth. In electronics, these voltage sources might not be shown. Okay. Invariably, we do not draw these voltage sources at all, number one. So, we do not show the voltage source, it is just not shown. I will show you how I am going to redraw this circuit in electronics. Number 2 is this point, the reference point is going to be shown as ground. Okay. So, this same circuit is going to be drawn now in electronics in this fashion. So, let us suppose this is the circuit and suppose this is not a circuit theory class, suppose this is an electronics class. We are no longer going to draw like this, we are going to draw it like this. So, if this had been 5 volts, I will just point out that this is 5 volts. Okay. Is this understood? This is going to be the new style of drawing for electronics. You are going to start with the power supplies at the top, right, and ground is going to be at the bottom. Ground is nothing much, it is just a reference point, right. We are all going to refer to ground, and then the circuit is going to be drawn, however it is. Any questions about this? This is going to be the style. This kind of a style also tells you that, I mean, immediately you know the direction of the current, because current is going to flow from top to bottom, okay. Higher potential to lower potential, higher potential is going to be drawn above, lower potential is going to be drawn below. Naturally, all currents are going to go downwards, Okay. They are all going to go from the top to the bottom. We are going to use this convention all through. Is that clear? Now, when we draw the transistor, this convention is implied. When I draw the transistor like this, notice that current is going to go from top to bottom. And remember, if you draw the transistor like this, it is very, very difficult to work out which way the current is going, okay, because it is not going from top to bottom anymore, it has to go like this, all right. So, this is not used, this kind of a drawing is no good. We are going to avoid this kind of drawing unless absolutely necessary. We are not going to draw like this, we are always going to draw like this. The PMOS, the P channel MOSFET, again current flows from top to bottom. Okay. The arrow in the device always points in the direction of the current. So, these are some of the conventions. Quick thing to remember is that the arrow of the device is always on the source, never on the drain. The arrow is always on the source, whether it is PMOS or NMOS, the arrow is on the source. Okay. The other terminal is the drain. Is that fine? And likewise, when you draw the BJT, the arrow is always on the emitter. Current flows in the direction of the arrow. So, in this case current is going to flow from top to bottom. This is NPN, and the PNP device current is again going to flow from top to bottom. And which is the emitter? The one with the arrow is always the emitter. All right, is this fine? So, with this introduction we are going to move forward. This is largely what I have talked about today as far as the transistors are concerned. I have only talked about symbols and conventions. Okay. In the next class we are going to actually start working with the transistor. We are going to introduce the transistor characteristics, and then we are going to start working with the transistor and start making circuits with it. Okay. Thank you very much and hope to see you soon.